Recording in progress.
The presentation is about a novel concept for a portable personalized ventilator with embedded air treatment system to disinfect, dehumidify, cool, and capture carbon at low energy. I am Nesreen Ghaddar, and this work is done in collaboration with Dr. Kamel Ghali and the PhD students Jean-Paul Harouz and Elvire Katramis, all at the American University of Beirut. For the well-being of occupants, outdoor air is typically treated by diluting the concentrations of water vapor and the carbon dioxide to acceptable levels, removing contaminants and cooling the resulting clean air stream before it is supplied to the indoor space. It follows that providing clean and cool air with low CO2 concentration to the entire indoor environment using the total volume ventilation techniques intensifies the burden of energy as it requires the treatment of large air flow rates into the space. What we are proposing as a solution to reduce the energy burden is basically to design an easily integrated compact ventilator supplying small treated air flow rates to provide acceptable air quality and comfort levels at reduced energy cost. So we focus on the occupant-centered ventilation strategies like coaxial personalized ventilation, which consists of one primary jet that is cooled and is clean, and another secondary jet consisting of disinfected room air. Such system provide the user with enhanced comfort and air quality levels while operating at low flow rates. For example, the primary jet would be about 2.5 liters per second, and the secondary jet would be at 8 liters per second. By minimizing shear stress at the boundaries of the primary clean jet, this configuration becomes effective in protecting the occupant and effective in clean air delivery to the breathing zone of the user at minimum flow rate of the treated air. For ease of retrofitting and practicality, personalized ventilators are designed to be ductless systems that extract the cool room air and supply it to the microenvironment of occupants. However, these systems lack the potential to treat the personalized ventilator supply air. So there are new techniques that are evolving in the research that rely on using desiccant material, such as metal organic frameworks, MUFs, for dehumidification, for decarbonization, and even for disinfection of air. When implemented in personalized ventilation system, operating at low flow rate, these desiccant systems are expected to be compact in size because I only need to dehumidify or decarbonize very small amount of air. So the combination of MUF-based desiccant techniques within ductless PV system results in a clean, dehumidified, decarbonized supply air to the occupant or user, the PV user. The burden of cooling of the PV supplied air and the regeneration energy that will be needed to regenerate the desiccant is done using a thermoelectric cooler. The simultaneous heating and cooling merit fulfills the need for the localized PV or personalized ventilation air treatment. So we have now a dehumidification process taking place, carbon removal, disinfection, as well as cooling, they are all combined in one compact portable unit. And we'd like to see how we can do that. So the novelty of this work resides in the multi-feature of the proposed system that decontaminates, dehumidifies, decarbonizes, and cools the air to be supplied locally via a ductless coaxial PV system, providing enhanced air quality and thermal comfort levels at reduced system size and energy cost. Implementing these air treatment techniques with ductless PV using low airflow rate is a win-win strategy, where the air treatment system allows the supply of cool, decontaminated air at low carbon dioxide and H2O concentrations at reduced system size. An integrated mathematical model of the system processes and components depicting the proposed system is developed and validated via experimentally published data. Then the model is used to adequately size that system, simulate its performance for a typical relaxed room air conditions. What I mean by relaxed room air conditions is actually the background air doesn't have to be at low temperature. It could be as high as 26 or 28 degrees centigrade when combined with the mixing system. The CO2 concentrations doesn't have to be at 1000 ppm. It could be relaxed to 2000, while still you are delivering the needs of the occupant directly in the microenvironment where it's needed. So to describe this system, this personalized ventilation system consists of a stationary coaxial PV system that extracts the room air, disinfects it from bacterial agents, treats it for water vapor and CO2 removal using muffs, while simultaneously cooling using a thermoelectric cooling unit and supplying it to the occupant breathing zone as shown in the figure. Two important advantages of using the thermoelectric cooling in this application is because it provides simultaneously the cooling on one side and then the heating on the other side that is required for the regeneration part of the airstream. So it can help in providing the regeneration energy required for muffs. Furthermore, it can easily switch the cooling heating mode simply by alternating the supplied current between these two streams. So highly stable muffs structures were used as platform for post-metallization and silvification employed as anti-microbial agents. They are used for the disinfection of both PV primary and secondary air flow jet. And you can see that the antimicrobial muffs is actually done through a loaded filter at the inlet of the ductless PV that draws the macroenvironment air into the compact system. So disinfected air that comes from that system is then divided into two air streams. The primary airstream passes over the cold TAC side to be cooled, while the water vapor and CO2 are simultaneously absorbed by the muff coated on the fins of the TAC unit. Resulting treated air is supplied from the V primary jet to the occupant at breathing zone, while secondary jet consists of disinfected room air that is supplied via the coaxial PV. To regenerate the muffs, another airstream is extracted from the room air that passes over the hot TAC side, absorbing desorbing thereby the species of CO2 and H2O that are purged into the airstream. The regeneration exhaust air is then discharged upwards away from the occupant going into the room air. Having the PV coaxial configuration ensures that we have reduced system size, as only the primary jet needs to be dehumidified, decarbonized, and cooled. This results in a low muff mass, reducing thus the system overall size and cost. Remember that if we want to provide, like when you have the coated fins with the muff now absorbing CO2 and the humidity, what you do in the system, you need to flip. So we end up with a cycle where the hot side and cold side go over a period of flipping. So they change from cool to hot and so on. And this will allow the system operation. And one of the findings that we will get out of this work is really finding how often do I need to rotate that system. All right, we go to the methodology where we have an absorption model. All these numerical models are based actually on heat and mass balances of the adsorption process using MUFs and the Peltier effect of the TEC model, the unit. These models are used to size the air treatment unit and determine its energy consumption to provide the supply air. So for the absorption model, we have a lump transient absorption model that is adopted in this study. The reason we say it's a transient because of the flipping that takes place in that cycle. And we have the mass conservation done for each species, whether it is CO2 or H2O. We are assuming that around each side of the unit, I have uniform conditions and I can do lumping here. I have also the energy balance on the air side, and then which is a typical balance. All what I need to feed in is the heat transfer coefficients depending on the airflow rate. The surface temperature, however, is the part here that has TS, that has the transient effect because of the frequency of flipping the device from one side to between one stream and the other. The TEC model, also following well-known models in literature, has been followed to be able to find out what would be the temperature of the cold side of the plate. Of course, to solve all of these equations, the absorbent temperature TS should be known. So the RC circuit that is equivalent for the system is used as shown in the figure on the right-hand side, and then we solve for that equation with the given inputs and outputs. Now, let's say we have the fully integrated model that has been, each component of that or process is validated for inputs and outputs with literature data. We need to have an approach to size that system, because I would like to find out what is the mass of MUFs that I will need for the effective capture of water vapor and CO2. And whichever mass is higher, I will take the higher mass to be able to do the process. So we know that the capture amount of each adsorbent depends on the personalized ventilator flow rate to be treated, the specific humidity and CO2 level of the air at intake, and also the expected exit conditions of the PV unit, the regeneration temperature for the MUF, and the cycle time. That is the period at which you will use for flipping the device from hot to cold and cold to hot. So point 1 and 2 about the flow rate and specific humidity and CO2 levels, the flow rate and supply air conditions, temperature, H2O and CO2 concentrations must provide the needed air quality and thermal comfort to the user. So I have a specific range to work with. I know that the user must have probably a relative humidity of 50%, CO2 concentration, not more than 400 or 500, depending on what you decide on the specs. A regeneration temperature in point 3 is actually for the adsorbent needs to be fixed at the minimum temperature that ensures that I have complete regeneration of the adsorbent using the macroclimate air. The macroclimate is the room air that is withdrawn at the intake of the ductless PV. And then point 4 about the cycle time, that is the flipping frequency at the TEC. It depends how frequently I flip that TEC unit. It would be probably of order of minutes or more. We will see from the case study that we will apply this system to. This is usually fixed to simplify the control and operation of the proposed system. So if we use generally a short cycle time, the adsorbent mass will decrease because frequently I am flipping and heating, removing the heat immediately from this. But if I'm using short cycle time, that means I will have fluctuations in the supply air temperature because the hot side, the hot vent side of the coated muff would be warm, and when you intake the room air at 26, it's for a short period of time, it's going to be warmer than usual, and it might not be able to deliver immediately to the user or the occupant the desired output temperature of the PV stream, which is typically at 22 degrees centigrade. So there's these are the advantage and disadvantage if I use a short cycle time, which means that I have an optimal time that can reduce the adsorbent mass while ensuring that thermal comfort of the user is met. And I'm going to use genetic algorithm because I have discrete points that I can calculate the objective function for me, which is the mass of the coated adsorbent mass. Remember, these muffs usually have high volume. So if you need lower mass, then your design works better for the system to be compact. Delta pen is the virtual conversion factor for the penalty term of the constraint, which is here the thermal comfort. For the thermal comfort, I'm going to use Zhang model in a scale +4 to -4, where +4 is very comfortable, -4 is very uncomfortable. I'll be shooting if I get the comfort level at 0, that's thermal neutrality. So, and I put the penalty function, and I want to make sure I satisfy the constraint during the system operation. So I put the system specs, typical relaxed macro environment conditions. I'll choose the temperature of 26 degrees centigrade, relative humidity, I allow it in the room to be 65%. CO2, I raise it to 1500 ppm, and then a concentration of 10 to the power 5 culture forming unit or CFU per meter cubic of airborne bacteria. I set that limit. So for the muff, I'm going to use MB of VE1NI. This is commercially available. It has exceptional carbon water capture capacities with a regeneration temperature of 75 degrees centigrade. The personalized ventilator supplied air, 23 degrees centigrade, with the flow rates that I mentioned before of primary jet at 2.5 liter per second and the secondary jet of 8 liter per second. In total, you have all that cool air coming to the front of the occupant, and that will provide the comfort. Relative humidity, 55%, and a maximum concentration of CO2 of 400 ppm, which is ambient level. And of course, the supplied air is exempted from bacteria agents because I've already put the filter at the intake to the PV. For the bacteria filter, you can use conventional glass fiber medium filter of 0.3 millimeter thickness with this material, silver mil 101 chromium per MI, bacteria deactivation efficiency of 100%. And then the TAC, I need to do the proper design of the heat sinks so that it can supply the 23 degrees centigrade, and it will work between the two temperatures in the 20s and the 75 degrees centigrade. So I will need electric power for this. The switching time, 10 minutes tended to provide a comfort level of 0.9 using the modeling that we have. We have used the integrated model. We simulated with the optimization algorithm to determine the optimal switching time that is able to provide the adequate level of local comfort at minimal system size. Switching time of 10 minutes ensured the highest comfort level close to 0.9, which is comfortable. For the switching time, the needed mass, the switching time with 10 minutes, the needed mass of the adsorbent was 60 grams to remove the needed amounts of CO2 and H2O and meet supply air conditions in the species concentrations. Note that this mass was mainly dictated by the water vapor capture requirements. The adsorbent regeneration temperature was provided by the TEC module, along with the needed cooling power for the primary PV airflow. For this current application, 2 TEC units with cooling power of 30 watt each were used, which also provide a temperature difference of 55 degrees centigrade between the two sides of the TEC. For effective heat dissipation at the hot side of the TEC units, they were equipped with a heat dissipation sink formed of 19 extruded fins with the following dimensions: 110 millimeter times 50 millimeter by 1 millimeter thickness and 3 millimeter spacing. And the needed 60 grams of mass were coated with a thickness of 0.15 millimeter. Yani with this is the design that I have. And as I said, the comfort level was best with 10-minute period for the flipping. When I try to observe how does that system operate, remember I have a transient period here where I want to ensure that the supply air, I cannot guarantee that the supply air is going to be at 23 all the time, all right? There is a certain period at the beginning of 2 or 3 minutes in which the supply air of the PV is going to be slightly higher than the 23 degrees centigrade. But this is why if we look at temperature of the PV jet outlet and the regeneration jet outlet, plotted here as a function of time over a period of 60 minutes, you notice that the temperature at the beginning of the cycle was about 27.2 degrees centigrade. But this only lasted, because that's an effect from the previous cycle. So this only lasted for 2 minutes, and still it offers the comfort, the desired comfort for the occupant. And this is the transient comfort. So people can tolerate slightly higher than 23 for a very short period of time. Given, of course, that you have a flow rate of 10 liters per second, just of jet flow towards the face and upper body. So this is the cyclic periodic solution of the temperature of the PV jet and the exit temperature for the regeneration jet. In addition, we are plotting the specific humidity for PV outlet and the regeneration jet outlet. And we're plotting also the CO2 concentration as a function of time, also the steady state, the steady periodic solution for the flow conditions exiting the supplied jet to the user and the regeneration jet outlet. We noticed the following. Both water vapor and CO2 witnessed a high concentration at the beginning of each cycle caused by the high temperature of adsorbent, which reduces the capture capacity for a short period of time. However, as adsorbent was cooled by the TEC, its capacity was restored and the target supply concentration was maintained throughout most of the cycle time, which is about 8.5 minutes. And only for 1.5 minutes you are violating this, but in total, it was mainly satisfying your requirements of 55% relative humidity and CO2 concentration above below 400. Actually, because we designed the system for water vapor to be absorbed at this level and used the mass for this, we ended up with CO2 adsorption even below the ambient conditions. So we ended up with CO2 level around 250 ppm. Remember, ASHRAE requirement is 1000 ppm in indoor spaces. This is due to adopting greater mass needed for water vapor adsorption. In conclusion, we've just proved the concept that it would work. We have not yet built the device, but the work on the prototype is dependent on funding, but it is something we are going to pursue. But in conclusion, personalized stationary air treatment unit consisting of coaxial PV system integrated with antibacterial filter and a MUFS-coated TEC unit. This device has been developed or proven. Experimentally validated mathematical models were adopted to minimize the system size while maintaining thermally comfortable conditions. The models were also used to simulate the system operation and determine its energy consumption, and it was found that the system required a total of 60 grams of adsorbent, while it needs 130 watts of electrical energy to properly operate, because I need to operate both the fans that drive the flow and the thermoelectric cooling unit so that I can regenerate and provide the cooling. And this is, for example, if you have an occupant in a space, the space is office space of 15 square meter. Normally, what you need to remove as load, because you will have to cool the whole air, dehumidify and so on, would be typically 15 multiplied by 70 or 100 watt per meter square. And so what we are doing here, we're just cutting this to 1/10 of its value because I'm only focusing on the needs of the occupant. A future work is necessary to assess, of course, the impact of implementing this system on the energy consumption of the background room air conditioning system. By this, I end up my presentation. Here is the list of references that we have used for developing of the concept and validating the component models. That's the second page of references. And I would like to thank you for listening to this presentation. I'm also acknowledging the support of Maroon Samaan Faculty of Engineering and Architecture Research Initiative at the American University of Beirut. Thank you.